Hello again. This is our last lesson in this unit on recurrence relations. We are going to talk about modeling recurrence relations and how sometimes that's more practical than using the recursive definition of those sequences. So here's an example. Imagine you want to save up for retirement, and we're starting off with a large deposit of $1,000. We're going to invest it at 6% per year, and we're going to compound it monthly. So every month we're also going to deposit $100 from my paycheck into the account. We're going to write a formula that calculates the amount in my account after n months. So the first month there is $1,000 in there, and then every subsequent month I'm going to take the amount, multiply it by 1.005, so that's 100% plus 0.5%, which I got by taking 6% per year and dividing it by the 12 months that are in a year. So that's how I get the additional 0.5%. So 1.005 times the term that comes before it, plus the additional $100 that I'm using from my paycheck and putting it into that account. All right, so I need to express the nth term in terms of n rather than the term that comes before it. That way I know how much is in there on any given month. So if you remember, this is a first order recurrence relation, so I can use that the nth term is c times my a value to the n plus d. And if you remember, my a value was 1.005. Okay, that means that the term that comes before it is c times 1.005 to the n minus 1 plus d. That becomes important. So there's the recurrence relation that I started with, and I'm going to make those substitutions. So that un becomes c times 1.005 to the n plus d, and un minus 1 becomes c times 1.005 to the n minus 1 plus d. And the same thing is going to happen that happened before. When I distribute this 1.005 into these parentheses, I'm going to get c times 1.005 to the n, not n minus 1, to the n, plus the 1.005 times d, for that distribution right there, plus the extra 100 on the end. And as before, both sides have c times 1.005 to the n added on. So I can simply subtract that off. And I get d on the left, and I get 1.005 d plus 100 on the right. So if I solve that, I get negative 0.005 d equals 100, so d equals negative 20,000. Okay, so I'm going to plug that into U1, and I'm going to find my value of C. So the first term can be calculated as C times 1.005 to the 1 plus D. I know my value of D is negative 20,000, so I plug that in. I know that my first term is 1,000, so I plug that in. And I get that 21,000 equals 1.005 times C. Dividing gets me 1.4 million over 67. That's my value of C. So not a pretty number, but I wasn't really expecting a pretty number. So the nth term is then 1.4 million divided by 64 times 1.005 to the n minus 20,000. So at the end of 10 years, which is what I was hoping to figure out, that's 120 months. So I look at the 120th term. That is 1.4 million divided by 67 times 1.005 to the 120 minus 20,000, and I get $18,017.25. Keep in mind that over the months I put $13,000 of my own money in there, so I've earned interest of $5,000, which is not too bad for 10 years, but nobody's going to retire in 10 years, so hopefully that will be worth a whole lot more. And if you want to find out the value for another value of n, simply try that for yourself. Try 30 years or 40 years or 50 years or however long you want to see. So that is modeling using recurrence relations. If you have any questions on this, please let me know, and I will see you tomorrow.